my work is about DiffMoog, a differentiable commercial-like synthesizer. And first of all, what is a synthesizer? Most of you probably don't really know. So a synthesizer is a device that makes sounds, okay, from scratch. I have a synthesizer here, and the first synthesizers were fully analog. I mean, they produce sounds through capacitance and inductors and analog devices. Later on, about 15 years later, the first digital synthesizers arise. And we have several types of synthesizers in terms of how the sound produced. So we have additive synthesis. Those of you who knows about Fourier theory and DSP, all this stuff. Fourier said that every sound you can reproduce using endless sine waves, yeah, with the stacking of sinusoids. This is one type of synthesis, which is very, how I say it, liquid. I mean, you can really get any sound, but it's very complex. And a much more popular approach is a subtractive synthesis. In the subtractive synthesis, we start with some sound source, some oscillator, which has many frequencies within, and then we start sculpting out the sound. I mean, take out some frequencies and take out volumes of these frequencies and stuff like that. Okay, so with me I have a Moog. This is Moog. This is maybe the most iconic synthesizer. The first one appeared in 1964, and this is the interface. And in the interface, we have here we have oscillators with all types of waveforms. We have their mixer, so we can change the volume, and we have a filter that takes off the frequencies, and we have also some control signals that sculpt the sound and change aspects of the sound along time. And we have also modulators, okay? So this is like a frequency modulation that we can do, okay? This is very typical to many synthesizers, and it sounds like this, okay? We have many types of, actually the sound space is huge, okay? With this device. Let's hear some. I play it, okay? I have a keyboard, and this is presets. What I play are presets that are all kind of pre-record. It's not recorded. It's the set of parameters are saved, okay? And then the synthesizer produce another sound. So what I wanted to show here, that it does have a huge soundscape, yes? But we have a problem, okay? The sound space is huge. I mean, I can take any knob. Knob is this rotary switch, okay? And we have endless of possibilities. So we have a question.
Which kind of the two kinds you mentioned before is this?
This is a subtractive synthesizer, yeah? And we have a question here. How to reverse engineer a sound, okay? Let's hear the aspects of the sound. Now, I tune it myself. So, I start with just an oscillator. Sounds like this. It is rich in harmonics, so I can take off and use filter. I can modulate it. This is frequency modulation. I can make another envelope so the volume keeps on and on. Okay, so with this demonstration, we have a huge sound space and how to reverse engineer a given sound. But we are in an engineering faculty, so we will ask the same question, but more engineering way. Given an input sound, get a set of synthesizer parameters that will produce a sound output that most closely resemble it. So what I mean, this is a sound matching task. And we go for an AI-aided sound matching. And I started with this model, okay? Oren Barkan, who is my instructor, had such a work before. And here we can see that we have a data set of audio and audio parameters. We put inside a neural network and the audio input. We get synthesizer parameters, and then we can make the loss on it. Okay, this one works really, really, really good. Okay, but now we ask the question, we equalize over the parameters, but actually we want to get a better sound. Okay, also, this method does not allow us to equalize a sound that is out of our same synthesizer. We want every sound. So our system now looks like this, and this is the work. We build a synthesizer, the DiffMoog, okay? And then we make the loss about the spectral audio directly. But this work needed to make the synthesizer differentiable, okay? So this is what very important about our synthesizer. So it is differentiable, it is fully subtractive, it's commercial like the same Moog that I just showed you, and it's modular. I mean, by modular, you can embed any module in a kind of a substrate of a matrix, and we can route however we want, and we can get many, many, many chains of sound as we wish, okay? The sound is computed from left to right, okay? Each module has its own processing. It's come to the right, process, and then we average the rightmost layer, and we get the sound output. Let's hear some sound examples that it's able to produce. Okay, so it doesn't work, I don't know why. One moment. Low volume, you get it. Okay, so, and this one is modulated by a square, by a sawtooth wave. And here we have a tremolo. We modulate the amplitude. Great. And here we have an envelope on the volume. Here we have an envelope over the frequency. And here we have a double modulation that is faster as we progress. These figures are called spectrograms, okay? Sorry for I didn't mention it. The x-axis is time, and y-axis is the frequency content of the sound a long time, okay? This is very common, and we want the loss function wants to equalize the target sound with the one that we get by the prediction. The color, it's the voltage or power, yes.
So you have two outputs, frequency and the amplitude.
Every column is just an FFT, a long time. It's actually STFT.
But the color also represents the intensity.
Yes. When it's brighter, there is more frequency content in that same in the specific frequency. Okay. What is the time? Okay, I have time. Okay.
Explain what is differentiable.
Differentiable means that I can take the synthesizer inside within an AI system and backpropagate gradients along it. So this is special. This is actually the work itself. There is no other synthesizer like this in the world. I mean, this is the most complete of its kind synthesizer. And I also give a platform for such a work and sound matching. So
I think it's good to explain the idea here. The point is that you want to do sound matching, so you want to define a loss function over the output of the synthesizer, okay? And you want to learn the parameters of the synthesizer, but in order to do that, you need to differentiate and backpropagate the error through the synthesizer. So you need to implement.
Okay, I'll explain 2 words. The spectral loss, okay, compares the sound directly. But in order to update the weights in the neural network, we need to backpropagate the gradients through the synthesizer. In order to backpropagate it through the synthesizer must have this special feature that it's differentiable. And it's implemented in PyTorch. And also many overcome of challenges that, for example, you need to use argmax for classification, but argmax is not differentiable. So we used Gamble softmax, stuff like that. Okay, challenges that we had along the AI. Do you know a bit around? Okay, so it's AI systems in general follow the gradients. You want to look to minimize some target function. In order to minimize it, you have to follow the gradient and find the global minimum or some local minimum that works for the specific task. And we will see that here in this task, it's a big challenge. What I see here is the actual neural network. Along with the synthesizer, we also published an open source code that provides the whole platform for sound matching, including a very sophisticated way to self-program the neural network according to the synthesizer chain that I chose. Okay, so the backbone is ResNet or any other net that you want. And for each parameter, I have an MLP layers that actually predict the parameter that we need, okay? Maybe it's a frequency, it's a modulation index of the frequency modulation, it's the ADSR envelopes, the MLP is a multi-layer perceptron, okay. It's linear layer, two fully connected layers. Yeah, it's two fully connected layers. Okay, so let's talk about the audio loss function. The audio loss function, be with me, don't read the English. We are in the faculty of engineering, don't forget. Until now it was music, so now some equations. Let's read it from the end, okay? At the end, we have the loss for the audio and loss for the parameters. Yeah, and we can use an alpha and beta to weight them. Okay, but let's talk about the loss of the audio because this is the most essence for this work. The loss for the audio is 3 sums. Okay, what are those 3 sums? We want to compare the spectrograms, but each spectrogram can be obtained via different windows sizes. Yeah, we have a trade-off between the resolution at the frequency and the resolution in time. Yeah, if you know some DSP. So we use multi window sizes to overcome this limitation. The other unique feature that we developed here is we compare not only at the sound output, but all along the signal chain. Yeah, if you remember from before, the synthesizer, at each module end, we have a sound output. So we can, at the sound output, just compare already there. So we can direct the behavior better. And the last one is several pre-processing functions, okay? We can just make L2 between the spectrograms. We can take the log, and then we get smaller variants, have a better utilization in the loss. And we have Wasserstein loss, which sums the loss along some line, okay? Why we need Wasserstein loss? Think about target sound and the sound prediction A and B. If we just do an L2, yeah, we just make the difference, we get the same, and we don't have any gradient data to follow. So what we do is A is closer to the target than B. But if you just do L2 between A and target and B and target, you get the same result. It's the same. If you just take L2, this is all zeros and the yellow line is 1. If you make the difference, it's the same. So you must use Wasserstein loss, which just sums along some line and then makes the difference. Okay, so then we can get some frequency. Okay, and now we see along sound matching the DiffMoog. We must use some preset. This is just a preset that I chose that reflects behavior like this synthesizer and endless other synthesizers. We have 3 oscillators, mix them. We can have an envelope shaper, yeah, along the volume. We have a filter, tremolo effect. Tremolo is a kind of amplitude modulation. And we have 2 low frequency oscillators that are control signals for other sound modules. And we can also route them differently, okay? And we want to look that we can predict that. So the training procedure, A is just the baseline. We trained only with the parameters loss. But then in B, we use the in-domain data, and we gradually shift between the parameters loss, ending with the audio loss. And with C method, we did it the same like B, but then we gave also out-of-domain data. And what we get, first of all, let's talk about the measure that we want to compare about. LSD is just kind of a similarity method for two images or spectrograms, yeah? We take the difference and then we use the Frobenius norm, which we want to minimize each cell, each value in the matrix, yeah? And what we see that the blue line is the baseline, the orange line is the B method along the in-domain data, and the light blue one is the out-of-domain data. And we can see that the LSD method for the out-of-domain data keeps low because we used the audio loss. So this implies that it's important to use some kind of audio loss, and it's also let us use out-of-domain data to make the sound matching task. But I hide a lot of challenges that we had along the actual results were not so good. We get a lot of challenging in the, we had a lot of optimization challenges, and a lot of time the behavior diverged of the, it can suit, I would say it, the convergence. I had a lot of problem in the convergence, okay? So why I had a lot of convergence problem? Maybe 2 years I worked about it, yeah, and we couldn't figure out, because these days AI do such amazing stuff, and to get a sound, what's the problem? Why does it doesn't work? And we realized something very interesting. If we fix every parameters to the real truth, yeah, and then only take the parameter or the modulation index, which is attribute of the frequency modulation, we see that the loss surface along these parameters, okay, those are this graph. Again, everything is fixed accept these attributes, and then we pass along all the values that are possible, and we get the loss function. So it's the real value lies in the deep, at the global minimum. And now we start from somewhere, and we want to get to this global minimum. But we see that the gradient, a lot of time, takes us to some local minima that just doesn't work. By the way, other attributes, like, ADSR, envelopes, did behave very nice in terms of convexity. I mean, it's like of a bowl shape that makes them work. But here, we see that there is a problem to actually detect the frequency or modulation index. And then we examined another thing, and we wanted to see that if we initialize our frequency here and use the gradient, we want it to come here. But this also doesn't work. Look at it. Look at the animation. What happens? It follows the gradient, but hop, it just doesn't lock in. And we realized, and for my best knowledge, no one said about it in other research around the world, that the gradient problem is not only here, not only at the micro level, but also at the micro, not only at the micro level, but also at the macro level. So here, we have a lot of noise in the gradient that does not allow us to converge. So to recap, we presented the most complete of its kind differential audio synthesizer. We provide an open source code to the community and to other universities and researchers to keep and push forward. But unsupervised sound matching is still an open problem. And this problem made me work very hard along with Noam. Noam is my instructor here. But finally, we just brought a new problem to the world. Yeah, like Fermat did. Kind of. I mean, not the whole world will deal with this one, but
I think the point is that there are still challenges in sound matching.
Yes.
So if anybody is interested.
It is a challenge, and
It's not a solved problem.
But can you explain in what situation you need, when you buy a synthesizer, there is saxophone sounds, piano sounds, somebody in the factory.
you won't believe how many people,
What do you need?
you won't believe how many people listen to some sound and they want to recreate it. But not Control-C, Control-V, copy-paste, but put it inside the synthesizer and play that sound. I mean,
Where do they hear it? On the radio? Or
wherever you want. Radio, disc, just rip it, take a sample and load it into such a system.
There are type of sound engineers that's their job, to manually tune
Yeah.
synthesizers based on, somebody comes and say, I want the synthesizer to produce a sound like this.
Yeah, but somebody did this sound, so you
No,
can maybe
a
you can
natural
ask him.
sound.
Natural.
Yeah, you
Take any sound.
you record some sort of
For some people, it's a secret, If you have a very big producer, a Grammy Award winning, this is his sound. How to recreate it? He won't tell you. Stuff like that. And I guess you can think about more usages, but this is the main usage.
And you cannot use intelligence, if you hear a sound, you cannot imagine what will be
You can.
the
You can.
ingredients.
You can with subtractive synthesis, but you have to be very, 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 very expert because the soundscape is huge. Think about, we have 26 knobs and switches, and everything is like הרכבה של פונקציות. Superposition of functions. You take f of x, and then g of f of x, and then h of f. So the end result is very unpredicted. unpredictable. It's very hard task. But AI do it better than humans, like so many things. With this one, by the way, not. With this one, about comparing the audio, not. But comparing audio.
Sound matching is still open.
Yeah.
The sound engineers still have jobs.
They still have jobs.
There's no app
Yes.
to replace them because I think we never saw a problem space, a solution space that was as complex as this one. So usually, I mean, none of our problems are convex. We never worry about it. So somehow we overcome. Sometimes it converts quickly, sometimes needs a little bit more work. This one is way more complicated than anything I personally saw before.
Also,
Isn't there a possibility to just reduce the resolution and then you won't have the
Adam, the main problem is that in AI, a lot of time, some local minima is good enough for a solution. I mean, take Mobileye, okay? You want to identify a bus. The AI system goes to some local minima, but it's good enough. It identifies the bus. Here, in this one, it must get to the global minimum to get the actual frequency. If it takes another local minima, it doesn't work. Not only that, our ears, the human ears, are much more sensitive than the eye system. If you see blue and light blue, it's the same. But the difference between peep and peep is in frequency is small. But in our ears, it's crazy. It's different.
I think one more thing to emphasize, because I'm not sure if it was clear, is that the point is not just to synthesize sound or to generate sound. That's an easy task to record something and generate it automatically. The point is to have it inside a synthesizer. So to have a synthesizer, a working synthesizer that reproduces some natural sound that we hear. So a musician would be able to play with it afterwards.
So why not to sample it? I mean, there is something called sampler. You sample a sound, and then you only change the frequency. So each key will produce the same sound, but with a different.
So in this work, we wanted to enable it in an existing synthesizer, or in our case, it's a new synthesizer that works like regular synthesizer. So a musician that is used to working with synthesizers would be able to work with this synthesizer and not having sort of learn a new instrument. So there are works where they kind of synthesize different sounds. There's a work by Google from I think it was a year ago that did very good work
2 or 3 years.
in generating sounds. So they can generate a lot of different types of sounds. But you give it to a musician, he wouldn't know what to do with it. And if he would, it's a totally new instrument. It's not a synthesizer. We wanted to basically do it for synthesizers that musicians work with.
Also, in samples, you can't keep and process it. I mean, you can process, but if you give it such a ability to a synthesizer, then you can continue and tweak the knobs and keep and craft the sound as you wish. And the most important, I want to say thank you for Noam, Tel Aviv University, Industrial Engineering, Delta Lab, and for all the everything, guidance, lab, resources, everything I need, this computer. Dr. Oren Barkan that instructed me very close, Almog El-Arar, another student, Professor Leo Wolf from computer science. And for the Tel Aviv University, it was a pleasure. I really recommend. Truly, I really enjoyed the studies. So thank you.